Good morning, children. So we continue with Earth's gravitational force. We all know by now that the Earth attracts every object near it towards itself because of the gravitational force. Why does it attract towards itself? The reason is the center of mass of the Earth is situated at its center. That is, the mass of the whole Earth is situated at the center. So the gravitational force on any object due to the Earth is always directed towards the center of the Earth. And because of this force, an object falls vertically downwards on the Earth. So if we throw a stone vertically upwards, this gravitational force tries to pull it towards itself, and thereby the velocity reduces. Due to this constant downward pull, the velocity becomes zero after a while. The pull continues to be exerted and the stone starts moving vertically downwards towards the center of the Earth under its influence. The stone is moving in a vertically upward direction, but the gravitational force is pulling it in the opposite direction. So due to this constant pull, the velocity keeps on reducing, and until it reaches zero. Once it reaches zero, the stone is totally under the influence of the gravitational force, and hence it starts moving vertically downwards. Now, according to the Newton's law of gravitation, every object attracts every other object. That we have understood in our previous lecture. But then you may be wondering, why then does the apple fall towards the earth but the earth does not move towards the apple? Actually, because of the mass of the earth and comparing the mass of the earth and the mass of the apple is lighter than the earth. Hence, it moves towards the earth. So, the next question is, what happens to the artificial satellites and the moon? Don't they fall down? Should they not fall down if they are attracted by the gravitational force? The earth attracts them towards itself, but unlike the falling apple, they do not fall on the earth. Why? The answer is because of the velocity of the moon and the satellites along their orbits. They do not fall towards the earth. It is this velocity that keeps them moving in their orbits. If this velocity was not there, they would have fallen on the earth, like the apple. We next come to this point, that is Earth's gravitational acceleration. Now children, this Earth's gravitational acceleration depends on Newton's second law of motion. Newton's second law of motion states that a force acting on a body results in its acceleration. So the gravitational force due to the earth on a body results in its acceleration. This is called acceleration due to gravity, denoted by g, and acceleration is always a vector quantity because it has magnitude as well as a direction. As the gravitational force on any object of the earth is directed towards the center of the earth, the direction of acceleration due to gravity is also directed towards the center of the earth. Now we come to the value of G on the surface of the earth. Here you can see that F is equal to G capital M upon R square. This we have got by Newton's law of gravitation, which we have already done. F is equal to mg. This is the force acting on the earth, and F is equal to ma, which we have already done using Newton's second law. Instead of A, we are substituting here G because here the acceleration is due to gravity. Yes, children. So Earth's gravitational acceleration, the derivation is here. F is equal to gmm upon r square. That is according to Newton's law of gravitation. F is equal to mg. That is Newton's second law, which is F is equal to ma. Now, equating both, you can see that m gets cancelled, and hence we get G is equal to G capital G m upon r square. Now here G is equal to G capital M upon capital R square, where R is the radius of the earth and M is the mass of the earth. G is equal to 9.77 meter per second square. G depends only on the mass of the earth and the radius of the earth. Hence, it is constant for all objects at a given place. Whether it be an apple, whether it be a book, whether it be an elephant, the gravitational acceleration will be the same. It does not depend on the mass of the object. It depends only on the mass of the earth as well as radius of the earth. So if in a given position you want to find the Earth's gravitational acceleration on various objects, we can understand that they will all be constant. Hence, G is equal to 9.77 meter per second square at a given place. It can vary. This can vary. How it varies, we can see in the next section. Variation in the value of G. Yes, children. So how can we understand the variation in the value of G? Now the first point is change along the surface of the earth. Will the value of G be the same everywhere on the surface of the earth? The answer is no. The reason is that the shape of the earth is not exactly spherical, and so the distance of a point on the surface of the earth from its center differs somewhat from place to place. Due to the rotation of the earth bulges at the equator and is flatter at the poles. Its radius is largest at the equator and smallest at the poles. The value of G, thus, is highest at the poles and decreases slowly with decreasing latitude. It is lowest at 9.78 at the equator. Now children, this can be better understood by this figure, where you can see the shape of the earth is like an orange, flatter at the poles and bulging at the equator. Why it bulges at the equator? We understood that it is the earth's rotation which makes the earth bulge at the equator. Now the distance from the center to the pole is lesser than the distance from the center to any point on the equator. That means the distance Cp is less than CE. Therefore, the gravitational force here will be more compared to any point on the equator. At the pole, the gravitational force is more, hence you get 9.832. Whereas at the equator, the distance is more, so the force will be less, which is 9.78. I hope you have understood. The second point is the variation in the value of g with the change of height. As we go above the Earth's surface, the value of r in the equation 5 increases and the value of g decreases. However, the decrease is rather small for heights which are small in comparison to Earth's radius. The Earth's radius is around 6,400 km. So children, we understand from this that as the height increases, the gravitational force decreases. We come to the third point about change with depth. Now here, the value of g also changes if we go inside the Earth. Now children, from this figure, you will understand that as we go towards the center of the Earth, the radius is decreasing. So you may feel that the value of g will also be increasing, but it is not so. Here you have to understand that g depends on the mass of the Earth. As you enter into the Earth, the mass of the Earth contributing towards the gravitational force also reduces. So as you go deep into the Earth, the mass of the Earth keeps on reducing. As you go deeper and deeper, you can see that the radius decreases. The mass of the Earth contributing towards the gravitational force also decreases. So, at the center of g, it is 0. So, when we move towards the center of the Earth, please understand that the gravitational force decreases. So now we can understand that as the height increases, as in the first case, then also g decreases, and with the change in depth, then also g decreases. Now we come to the second point, next point, that is difference between mass and weight. What is mass and what is weight? Mass is the amount of matter present in the object. We have been learning this since long. It is the amount of matter present in the object. Whereas weight is the force with which the earth attracts the object. Please understand, weight is the force. It is a force, or the gravitational force acting on an object is called weight. The SI unit of mass is kilogram, whereas SI unit of weight is Newton. Why is it Newton? Because it is force. Weight is the gravitational force. Now, mass is same everywhere because it is matter content. Whereas weight is not constant everywhere. It depends on the gravitational force, that is G. So we understood that G is not same everywhere. It keeps changing, and hence the weight is not same everywhere. Here, mass is a scalar quantity because it has only magnitude, whereas weight is a vector quantity because it has magnitude as well as direction. So this is the distinguish between question of mass and weight. These are the 4 points. Note it down. Our next topic is free fall. After reading this paragraph, you will come to understand that whenever an object moves under the influence of the force of gravity alone, it is said to be falling freely. Thus, the released stone is in free fall. In free fall, the initial velocity of the object is zero and goes on increasing due to the acceleration due to gravity of the earth. During free fall, the frictional force due to air opposes the motion of object and a buoyant force also acts on the object. Thus, true free fall is possible only in vacuum. So, understand that whenever an object moves under the influence of the force of gravity alone, it is said to be falling freely, and this is possible only in vacuum. For a freely falling object, the velocity on reaching the earth and the time taken for it can be calculated by using Newton's equation of motion. Now, this is a very important definition which is often asked, what do you mean by free fall? So, we have to understand that any object under the influence of force of gravity alone is said to be falling freely. That means there is no other force acting on it. It is purely under the force of gravity, and this is possible only in vacuum. For calculating the motion of an object thrown upwards, acceleration is negative. That is, it is minus g if the object is moving upwards. The moon and artificial satellites are moving only under the influence of the gravitational field of the earth. Thus, they are in free fall. This is a true or false question. The moon and the artificial satellites are moving only under the influence of gravitational field of the earth. Is it true or false? It is true. They are in free fall. Our next point is escape velocity. Now, what is escape velocity? The velocity with which an object is able to overcome the downward pull by the earth and can escape the earth forever and will not fall back on the earth. This velocity is called escape velocity. That is, it is escaping the gravitational pull of the earth. An object going vertically upwards from the surface of the earth having an initial velocity equal to escape velocity escapes the gravitational force of the earth. The force of gravity being inversely proportional to the square of the distance becomes zero only at infinite distance from the earth. This means that for the object to be free from the gravity of earth, it has to reach infinite distance from the earth. That is, the object will come to rest at infinite distance and will stay there without falling down.